Coffee is a beverage brewed from the roasted and ground seed of tropical evergreen coffee tree that are originated in Africa. Beside water and tea, coffee is one of the three most popular beverages and one of the most profitable commodities in the world. In the 15th century, wild coffee plants that were likely from Kaffa, Ethiopia, were transported to southern Arabia and planted. Nearly 90% of coffee consumed worldwide is produced by two plant species, Coffea arabica, Arabica coffee, and C. canephora, the Robusta coffee. Compared to Robusta, Arabica is thought to provide a milder, more flavorful and aromatic beverage. Arabica requires a cool subtropical temperature and grows more widely than Robusta, but it is more susceptible to pests. Arabica must grow at higher altitude, requires high humidity and very specific shadow. Robusta bean is harder, more convex and rounder than other coffee beans, which can grow at lower altitude. Robusta coffee is often the bean of choice for low-cost commercial coffee brand since it is easier to grow, contains twice as much caffeine as Arabica, and less expensive. Caffeine is a naturally occurring chemical that can be found in the leaf, seeds, and fruit of at least 63 different plant species across the globe. It belongs to a class of chemicals called methylxanthines. Coffee, cocoa beans, cola nuts, and tea leaf are the most well-known sources of caffeine. The caffeine content depends on the serving size, type of product, plant variety, and preparation technique. Although there are countless beverages that use coffee as their base, caffeine, which is an alkaloid found in coffee, is primarily responsible for its energizing effect. Caffeine is popular because it is a pharmacologically active chemical and a mild central nervous system stimulant. Additionally, drinking coffee has been linked to both positive and negative health effects. In general, moderate intake, 3 to 4 cups per day, is associated with a lower risk of Parkinson's disease, liver cancer, type 2 diabetes, and cardiovascular diseases, and having longer lifespan. Overindulging in coffee can result in sleep difficulties, anxiety, jitteriness, and heartburn.
Okay, for the principle of the UV spectrophotometer, during the measurement of the caffeine content in coffee, the molecule in the sample will absorb light at a different wavelength within the color spectrum, then providing information that can then be used as a quantifiable data for determining the concentration of caffeine. The second one is a series of caffeine. Standards are analyzed in the region of absorption and a beer law plot is prepared to determine the concentration of the caffeine. The third one is the caffeine absorbed radiation with a wavelength around 260 nanometer, where the conjugated system is one containing two double bonds separated by a single bond. Okay, for the application of the UV spectrophotometer into this caffeine determination, the first one is it must have desirable clean raw, rested appearance, attractive flavor, good cup taste which is balanced in acidity and body, and also the level of caffeine. The second one is the quality of coffee is dependent on many different factors, but color perception is often as a prime component of a consumer choice. The third one is the UV light can facilitate the quantification of the caffeine content within a certain legal limit.
The coffee samples were collected or purchased from volatile zone of 5 different orders, namely Bolososor, Bolosopom, Kaindo Koisha, Sodo Zuria, and Humbo of model farmers. Those areas are selected purposefully because of two reasons, which are due to their productivity and their geographical location. As for the materials and chemicals, the apparatus and materials are UV visible spectrophotometer, 1 cm quartz cuvettes, droppers, ring stands, vacuum pump, Buckner funnel, filter paper, 0.7 cm of iron rings, separatory funnel with 125, 250 and 500 milliliters, 50 milliliters of graduated cylinders, a Erlenmeyer's flask, pipettes, round bottom flask with 250 milliliters, dried volumetric flask with 25, 50, 100 and 250 milliliters. As for the chemicals, are standard caffeine powder, chloroform, grinds coffee, sodium carbonate, distilled water, dichloromethane, and sodium sulfate.
Preparation of standard solution. 200 mg of standard caffeine powder were dissolved in 200 ml of distilled water to create a 1000 ppm stock standard of caffeine. Working standards were met by pipetting 25, 12.5, 10, 7.5, 5 and 2.5 ml of aliquots of the stock standard solution into distinct 50 ml volumetric flask, dilution to volume with filtered water, and stirring with a magnetic stirrer for 30 minutes. A UV spectrophotometer were used to measure the absorbance of each solution at the absorption maximum of 260 nm. The calibration curve was created by plotting the absorbance value versus concentration. Caffeine extraction procedure. From each working standard or sample solution, a 50 ml of aliquot was obtained. A separating funnel was used to deposit this aliquot, and 25 ml of dichloromethane was then added. The funnel was flipped at least 3 times, with each inversion being followed by a vent to remove caffeine. The solvent layers were mixed after the dichloromethane layer was removed to a clean flask, and the extraction process was done twice more.
Sample preparation. In a flask, 1 mg of dried and ground sample was combined with 100 mg of magnesium oxide and 1 ml of distilled water. The mixture was heated in a steam bath for 20 minutes. 5 ml chloroform was added and sonicated for 50 minutes before anhydrous sodium sulfate was added. The mixture was filtered through filter paper and washed 3 times with 5 ml dichloromethane. Using dichloromethane, the final volume was reduced to 50 ml. Quantitative determination of caffeine. A UV spectrophotometer was used to perform quantitative caffeine analysis. The lambda was calculated by scanning the standard solution from 200 to 600 nanometer and calculating the obtained result show an absorption spectrum with a single intense absorption band in the UV range at lambda max equal to 260 nanometer. To obtain the linear range of sample analysis, a standard linear calibration curve was run. The correlation factor was with accepted value greater than 0.996 and the standard calibration curve was linear over the range 10 to 50 ppm caffeine. The standard curve was used to calculate the quantitative amount of caffeine in the sample in ppm.
For result and data analysis, from the Journal of American of Applied Chemistry, the figure 1 shows the calibration curve of the absorbance and caffeine concentration. From the curve, the pure Lambert law can be obtained, which is the absorbance is directly proportional to the concentration. Next, the table 1 shows the caffeine concentration of the extracted sample. From the linear regression of concentration and the absorbance, give the factor 34.5. The concentration of extracted sample in ppm can be obtained by using the formula concentration, which is 34.5 times with the absorbance. There are 5 types of coffee that need to be calculated concentration in ppm, which is Bolsoso coffee, which is A, Bolosa Bomba coffee for B, Kindo Koisha coffee in C, Soda Zera coffee for T, and lastly E for Humbo coffee. For example, in sample A, the absorbance is 0.98 will multiply with the 34.5 give 33.81 concentration in ppm. Same goes with other sample, it should be multiplied with the 34.5 and give result 37.60 for B, 33.46 for C, 36.91 and 35.19 for D and E. So, it can conclude that the higher the absorbance, the higher the concentration of extracted sample in ppm.
Using the given equation, The final caffeine content of the beverage on the test is calculated from the concentration of the extracted sample solution. The caffeine content per ml is calculated by dividing the value obtained from the equation by the volume of the drink. The caffeine content of the coffee samples range from 501.97 to 564.07 mg per liter, according to the results. Caffeine levels in all 5 coffee samples studied are nearly identical. However, caffeine levels in sample B are the highest of any of the coffee sample studied. Sample A and C, on the other hand, have the lowest caffeine content of the coffee sample study. Caffeine content of samples D and E has an average amount of caffeine, as shown in the table above.
From the results and data of the analysis, now we know that the amount of caffeine in all 5 samples ranges from 501.97 mg per liter to 564.07 mg per liter. According to my research, the FDA or Food and Drug Administration recommends 400 mg of caffeine per day for healthy adults, while pregnant or nursing women should limit caffeine to 200 mg. Thus, we can simply say that the range of caffeine in all 5 samples are considered moderate. All 5 coffee samples from Wolaita zones that were tested for caffeine were almost all in the same range, where Boloso Bomba coffee has the most caffeine among Wolaita zone samples with 564.07 mg per liter. Next is Kindo Koisha and Bolsosor coffee have the least caffeine with 501.97 mg per liter and 507.15 mg per liter respectively. And from the table 2, from the previous slide, shows that Sodo Zuria and Hamburg coffee have average caffeine levels with 553.66 mg per liter and 527.84 mg per liter respectively. Okay, you might want to know why and how come each coffee contains different amount of caffeine. Worry not, because I will share the factors. The first one is the type of bean, which is related to location. Where the coffee beans were grown can come into play. Coffee beans grown at a higher altitude will typically have less caffeine than those grown at a lower altitude. The 2 primary types of coffee beans are Arabica and Robusta. Take for instance the world's most popular coffee bean, Arabica, and its well-known counterpart, Robusta. Arabica grows best at around 1,300 to 1,500 meters, whereas Robusta grows at a maximum altitude of 600 meters. Because of this, Arabica tends to contain less caffeine than Robusta. The second factor is coffee bean roasting time. Darker roasts give a higher caffeine spike, right? Nope, it's a common mistake to think that. During the roasting process, the coffee's caffeine level stays pretty much the same. The longer a coffee bean is roasted, the less dense it will be. This is because coffee expands when it is roasted and loses water weight. This means a scoop of coffee grounds has more dark than light grounds, and because you use more coffee grounds, darker roasts tend to taste richer and stronger because of this. Just a bit of a side note, only a small amount of caffeine is lost when the coffee is roasted for longer, so this isn't as much important as the other factors. The third factor is the grain size. The size of the grain has a big effect on the coffee you make because it lets the flavors and smells out from the coffee bean. The finer the grain, the more water is exposed. With more exposure, more caffeine will be extracted. Therefore, it will produce coffee with higher caffeine content. Next factor is the brewing method. Coffee made with methods that fully immerse the coffee grounds has more caffeine than coffee made with pour-over methods. With full immersion methods, the greens can also stay in the water longer if that is what the brewer wants. With longer brewing times, more caffeine is extracted from the coffee grounds. Also, brewing with hotter water extracts more caffeine. And the last factor is the matrix effect of UVA absorption, where it can cause interference during the analysis.
As shown, the selected method for this investigation is spectrophotometric analysis due to its speed, high precision, and reproducibility. The amount of caffeine investigated in 5 samples of the volatile zone had moderate to medium caffeine concentration when compared to the value reported in the literature for various coffee kinds. Additionally, the coffee has been evaluated and found to have an availing flavor and acceptable cup taste and good stimulant potency, which make it one of the highest commercial yields in the region and is entirely organic coffee. When all of this considered, volatile zone coffee has high quality in terms of cup flavor and caffeine content. Given the widespread use of caffeine, it is crucial to get accurate data on the amount present in various meals. Due to its stimulant effect and other factors that are still causing health concern, many consumers choose to partially or completely avoid caffeine. As a result, decaffeinating coffee is an important industrial procedure. For the additional information, according to the Agricultural Office statistic, volatile zone produce a lot of high quality of coffee due to usage of organic fertilizer by the coffee producing farmers. The result of this study have revealed that the coffee flavor as experienced at the Jivina Buna of the region and the volatile ECX office is quite unique and has relatively low quantity of caffeine.
Step of precautions. Repetition of experiment is very important in order to get an accurate result and conclusion. More data collected, more accurate conclusion is. Eye of observer should be perpendicular to scale while recording a data to avoid parallax error. Record the results systematically. Data collector may be influenced by another external factor such as recording a data with a wrong decimal places. For example, 10 Kelvin written as 1 Kelvin due to misunderstanding. Clean apparatus should be used to avoid a chemical reaction that will disturb a concentration caffeine that analyzed.
And that is all from us. Thank you. Have a nice day.